they found the gravitational wave. They put out they tried to, there was a waveform, they tried to make it interpreted using an audio signal. Okay. So it sounds something like you could train a claim that this is what it is.
Okay, so it's my pleasure to introduce Dr. Yogesh Wadadekar, who is a scientist from NCRA of PRFR. Yogesh has done his BTech from IIT-Bombay and then his PhD from IUCAA. Then he worked on his postdoc. He did his postdoc from USA and France, and then he returned to India to take a position at NCRA. He has a lot of experience working with different types of telescopes across the globe. And today he is going to share with us the challenges that he has faced in the acquisition, processing, visualization of petabyte size data. So, with this,
Thank you, Rahul, for inviting me here and for hosting me so graciously. It's a pleasure to visit this institution and talk to the students and faculty members over here. Today I'm going to talk about petascale computing challenges in astronomy, and more specifically in the field of radio astronomy, where such a challenge has been thrown up. And I will describe how we are working towards solving that challenge. So, the area of study of astronomy and astrophysics is very simple. We aim to study absolutely everything that is above the Earth's atmosphere. Okay, even we start studying by the Earth's ionosphere, and we study the whole universe, and we seek to understand everything that is there in the universe. So this cartoon shows us very briefly how the universe operates. Is there a laser pointer? So at the beginning of time, you had the Big Bang, which was one gigantic explosion in the universe. So that is here. That created all the matter that we know in the universe, but the universe at that time was so hot that the matter was in the ionized state. Okay? It was one giant cloud of plasma. But as the universe expanded, that plasma cooled. Eventually it cooled to a point where electrons and protons could come together and form hydrogen atoms. Once they formed hydrogen atoms, that is at this point, about 400,000 years after the Big Bang, at that point the universe went completely dark because there was no longer any hot plasma to emit light. There were these atoms of hydrogen everywhere in the universe and nothing else. But of course, due to gravity, these atoms of hydrogen converged together and they came together to form large clouds of hydrogen, which eventually collapsed under their own gravity and formed stars. So the first stars emerged about 400 million years ago. And after that, you had a long sequence of the story of the evolution of galaxies and everything within it, like stars and planets and so on. So the remaining sort of 13.3 billion years is this story, and it is primarily this story that the astronomers of the world are trying to tell. Okay, so I'm going to play for you now a video which is a simulation of the evolution of the universe. Okay, so you can see here that we are in 1 second we are going to jump forward by 100 million years. We've simulated the entire universe on a computer, What you see, all these blue threads that you see are giant strands of dark matter. And as time goes on, we are actually changing the camera angle, so we are sort of seeing the universe from every side. But as time goes on, eventually you will find that there are certain regions where the density of matter increases. These are the areas in which you will form the first galaxies, and today you will see the largest galaxy clusters. After some time, stars begin to go off, begin to form and explode as supernovae. These are these sort of red explosions that you see all over. At the same time, you also have a lot of feedback from what we call active galactic nuclei, which are supermassive black holes at the centers of galaxies that give out even larger amounts of energy. So this leads to pollution of the intergalactic medium with metals. Metals, by metals I mean everything except hydrogen and helium, which has been produced inside stars. So when the supernovae go off, all the metals that are there in the universe, so the red color, the magenta color here indicates the pollution with metals. So wherever you have magenta color, that region is rich with metals. Remember, we've now reached about 9.5 billion years since the Big Bang, still about 4 billion years to go. Now we are beginning to see a universe that resembles the universe that we see today. And in a few seconds, we will reach a stage where the time clock will read 13.7 billion years, and we will have reached the present day universe. So this is somewhat like the present day universe. The universe is, the largest structures in the universe are called what we refer to as superclusters, and these are these structures that you see here today. So this was done by a very large collaboration called the Illustris collaboration. I showed this simulation here because there has been a tremendous amount of work that went into producing this simulation, in which a supercomputer was used to run a computer program for about 6 months. This was done about 4 years ago. And every few years, astronomers come up with better and better numerical simulations that do a self-consistent, provide a self-consistent picture of the evolution of the universe over its entire lifetime. The simulation that you saw was about 4 years old. I'm sure that in a few years, we'll have an even better simulation which takes in all the observations that we have made so far and make sure that the simulations are consistent with what we know of the real universe. Right. So what is astrophysics? Just to sum up, astrophysics is the application of the laws of physics to the study of everything that exists in the universe. It might be the sun, it might be the planets that go around the sun, other minor things like comets and asteroids, stars of various flavors, brown dwarfs, white dwarfs, neutron stars, black holes, and so on. There is now a new exciting field of study which has emerged in the last decade. It's the study of extrasolar planets. These are planets that go around other stars in our galaxy. We study the stuff between stars. We call that the interstellar medium. We study galaxies. We study galaxies, groups of galaxies. So the Milky Way sits in a group called the local group. We study galaxy clusters, like the one you saw at the end of the simulation. We study active galaxies of various flavors, like quasars. We study the stuff between galaxies, which we call the intergalactic medium. We study the cosmic microwave background. We study gravitational waves. So all of these studies were mostly with electromagnetic radiation, but we have now opened a new window in the last few years of trying to study the universe in gravitational waves. We study matter that we can't even see, but we can only detect through its gravity, which is dark matter, and another manifestation of a sort of anti-gravity, which we refer to as the dark energy. We even tried to study the universe as it existed a fraction of a second after the Big Bang. This is known as the inflationary model of cosmology, and that we do although we can't detect it or even see it directly. And of course, astronomy is the field that is related to the search for extraterrestrial intelligence, to try and find other civilizations like our own and try and detect them and possibly establish contact with them. So it's a very, very broad field of research. It's a field of research that is carried out in many different countries of the world. India is one of the big names in astronomy, and particularly in radio astronomy, which I will talk about in a few minutes. So why does this even work? I mean, why are we so successful in understanding the universe? So Einstein once made a statement that the most inexplicable thing about the universe is that it is explicable, which means that although it's so huge, unimaginably huge and unimaginably complex, we can still make sense out of it. That itself blows Einstein's mind. So this can happen because, as far as we can tell, the laws of physics are universally applicable. Same laws, Newton's law of gravity and other things that you are familiar with on Earth, apply everywhere else and apply in an unchanged way. It's not as if Newton's gravitational constant has a way different value in some other galaxy. It doesn't. It has to have nearly, very nearly, or exactly the same value. So although there are a number of unsolved problems in astrophysics, that's why it makes for a very vibrant field of research. I mean, all you have to do is scan the newspapers, and every few days you will find some new news about some new discovery in astronomy. So although there are many new problems that are being posed and remain unsolved also, like dark matter and dark energy, but there has been a lot of progress also in solving unsolved problems. So we live in interesting times. Astronomical data is special in two respects. The astronomical data sets are increasing in size exponentially. You might say that there are many other fields in which data size is increasing exponentially, but there is one aspect that makes astronomical data quite special, is that unlike in most of the other fields, astronomical data have no economic value. Okay? And this is the reason that they can be and are freely shared internationally. In fact, a lot of effort is put in by astronomers to make sure that the data that they have obtained from their telescopes, from the ground and in space, is universally available, not just available, but easily accessible, because there's no point in putting out a petabyte of data. Here's a petabyte of data. You have to give people tools and software to process that data, to visualize that data, and so on. So all that is also being done in some sense. Okay. So now I'm going to switch gears and talk about the use of computing in the field of radio astronomy, with a special focus on a new telescope that we are now starting to build, which is called the Square Kilometre Array. But before we get there, let me tell you a bit about the electromagnetic spectrum. So most of what we know about the universe today is by observing photons that we receive from the sky. Okay? You know, visible light, the sun gives us lots of photons. There's some photons streaming in right here. The sun is a very bright source of visible light, but it's fainter at other wavelengths. There are many wavelengths of light or many frequencies of light that are not accessible to the eye. The eye is not sensitive to them. This might be wavelengths which are longer than the wavelength of red light, which we call as infrared radiation, radio waves and long waves. The visible window is a very thin slice of the spectrum of electromagnetic radiation. At higher frequencies and shorter wavelengths, you have ultraviolet, X-rays and gamma rays. Now the entire electromagnetic spectrum is now being studied by astronomers. This was not the case 100 years ago. 100 years ago, we were only doing optical astronomy, maybe a little bit of infrared and a bit of ultraviolet. But now we are doing gamma rays, X-rays, ultraviolet, optical, infrared and radio. Okay? We are studying the universe in all of these bands. If you focus on the radio, unlike the optical, which spans about a factor of 2 in wavelength or frequency, in the radio you span a very, very large range of frequencies, okay, going from very low frequencies to very high frequencies. Most of radio astronomy is done in this range. Okay, so you start at sort of the sub-gigahertz, 100 megahertz level, and you go up to 100 gigahertz or sometimes up to terahertz. Okay, so this, and of course beyond is optical and so on. So this is a fairly wide range of frequencies that we study the universe in. I'm going to be talking about a telescope that operates roughly between 10 raised to 8 and 10 raised to 10 hertz. Okay. So a number of large radio telescopes have been built in the world over the last 70 years. I show here 3 of them because the telescope that we are going to build is going to be a superset. It's going to supersede all of these. So at the lowest frequencies, at frequencies of 150 megahertz and below, the world's largest telescope is called LOFAR, short for Low Frequency Array. This is just one of the stations of LOFAR. They have many other stations. And you'll notice that at low frequencies, the radio telescopes don't look like satellite dishes. They look more like dipole arrays, and we'll see pictures of those in a minute. So this is a dipole array built by LOFAR in the Netherlands. When you go to somewhat higher frequencies, then it becomes optimal to use a dish in place of a dipole array. And in India, near Pune, my institution operates the world's largest mid-low frequency radio telescope, the giant meter wave radio telescope. You can see 3 dishes of the GMRT here. Each dish is 45 meters in diameter and it is fully steerable. You can turn it in any direction. There are 30 of such dishes that have been built and are spread over a fairly large area in the northern part of Pune district. The longest baseline, which means the largest distance between 2 telescopes, is 25 kilometers. Okay, so it's a fairly large telescope with excellent resolution, excellent frequency sensitivity, and so on. We're just in the process of completing an upgrade to the telescope that will keep it competitive for the next 10 years. And it is an open access facility that is available to astronomers all over the world. And so we have astronomers from 35 countries who come and use this telescope. At higher frequencies than the GMRT, the most competitive telescope in the world is the Jansky Very Large Array. It's located in New Mexico in the United States. And this has been running since 1980. This has been running since 1999. This has been also upgraded a few years ago. So this also is now a very competitive large radio telescope. All of these telescopes that I showed you are what we refer to as radio interferometers. So what we do is we observe the same radio source with 2 dishes, and we combine the signal from those 2 dishes in order to improve the resolution and the sensitivity of the instrument. The simplest radio interferometer consists of 2 elements. So let's say you have a dish here and you have one more dish here. The dishes are pointed in this direction. They're receiving radio waves. The radio waves can be thought of as a plane wave. So it will hit this detector first, and after traveling an additional distance of v sine theta, okay, so after a time v sine theta divided by c, the velocity of light, this radio wave will hit this other detector. Now this is a fixed delay depending on which direction you're pointing in, and can be corrected for easily. So if you correct for that delay, which means you delay this signals until this wave hits here, and then you combine the 2 signals together, you basically measure the voltages that are induced at the focus of the telescope by the electromagnetic radiation multiply complex conjugate voltages together and store them as visibilities. What every visibility gives you is a fringe. So this is actually equivalent to a Young's double slit experiment, okay, which some of you might remember from your school and college days. This is exactly equivalent to the Young's double slit experiment. So what that produces for you, every pair of, so these are now many dishes. So any two dishes that you take will produce for you a fringe pattern, just like you see a series of fringes in the Young's double slit experiment on the screen. The orientation of the screen will be dependent on the orientation of this baseline, the angle that it makes, let's say, with the horizontal, and the spacing between bright and dark fringes will depend upon the spacing of the two dishes in the baseline. So if the dishes are separated by a short distance, the fringes will be widely separated. Okay, if they're separated by a short distance, the fringes will be widely separated. If they're separated by a relatively large distance like here, the fringes will be close to each other. Now, because of the pattern that we're actually not detecting, we're only detecting fringes. We are not actually detecting the radio source of the sky. So it can be shown that mathematically that what we are detecting actually is the Fourier transform of the intensity on the sky. Okay? So if we take an inverse Fourier transform, then we'll be able to reconstruct the image of the radio source that we are observing. This may seem simple in principle, it is, but in practice it turns out to be extremely difficult because you are all your measurements are noise dominated. It's a very noisy measurement, and therefore it becomes extremely difficult to carry out this exercise of doing the inverse Fourier transform and imaging whatever you see. Therefore, effectively every telescope becomes a software telescope which is easily upgradable and reconfigurable. So by changing the software algorithms for converting these fringes into images, you can improve the performance of the telescope without touching any hardware at all. But this also poses a challenge. I mean, if you have buggy software or if you have non-optimized software, then that is going to reflect on the performance of the radio telescope. It's not going to perform the way it should. But of course, the software can be improved. It is relatively easy to upgrade software than to upgrade hardware, and it is endlessly reconfigurable. So when we build a telescope, that's why radio telescopes once built, the hardware like the dishes and so on are rarely changed. But everything, the electronics backend as well as the software are continuously upgraded so that radio telescopes once built can remain in use for more than 50 years. So we are trying to build a radio telescope for the 21st century, something that is going to take us more than 10 years to build only for what we call as the phase 1. But phase 1 is just 10% of the full telescope. So to give you a picture of what is going to be built, I'm going to just show you a video for the square kilometer array. Okay? What we are building now are two kinds of telescopes. One is this dish-based structure, and the other is these dipole antennas. Okay? These are very tall dipole antennas. You'll see another variant of that in the video. This video that I'm showing you was made about 5 or 6 years ago, at a time when people were trying to garner a lot of support, so it's a little bit over the top, but it is quite spectacular. Okay, so what you see here are dishes. There will eventually be between 2,500 to 3,000 dishes. Each dish is about 15 meters in diameter. And what you're seeing now is what we refer to as the the central part of the array, and every dish is individually steerable. It can point to whichever direction you want to point it to. So here they are, the dishes. This is referred to as the focus. This is the point where the radio waves, after being reflected, will get focused onto one point. The dishes, as you notice, can point in any direction you want. So what we looked at are a 5-kilometer circle here. Now these are dipole arrays. We are going to build this design has now changed from what was made in the video, but the functionality remains the same. This SUV is shown there just to give you a scale for how big this thing is. Again, this will also there will be a third technology which is not going to be built in phase 1. It will only get built in phase 2. This is referred to as a dense aperture array. Again, you have dipoles, but they are very closely spaced. So this is one dense aperture array station, this is another, this is a third, fourth, fifth, and so on. Each of these telescopes will have a dense central core. So there will be many detectors which are closely spaced from each other. But there will be arms that we are going to sort of fly along one of the arms. Okay. And you see that every few kilometers there is a dish and there is a bunch of dipoles and dense aperture arrays. We are now 150-200 kilometers from the core, but that's not all. We will build many such structures, keep on going 500,000, 2,000, up to 3,000 kilometers from the central core. Okay, so people thought that yes, this would be a good thing to have, but it was when they spec'd it out, it turned out to be mind-blowingly expensive. Okay. So they said, okay, let's build this in 2 phases. Let's build 10% of it first. Let's, instead of going out to 3,000 kilometers, let's go out to 200 kilometers. Let's build most of the inner core, and let's build 5 arms, but only out to a distance of 200 kilometers. And but of course, even this will be spectacular. So the rest of the talk will talk mostly about what we refer to as SK1. Okay. So the 2 simplest metrics, yeah.
Sir, is this plant in Pune?
No. This I'll come to that in this comment. So how will the SK be better? So what we are building, the 10% is called SK1, and these are the 3 telescopes that operate in different frequency ranges and their sensitivity. So this is LOFAR, the telescope in the Netherlands. This is the upgraded GMRT, and this is the VLA in the US. SK phase 1 will already be approximately 10 times better than what we have, the best that we have today. If we go to the SK phase 2, which was the video that you saw, that will be about 100 times better than the best that we have today. Okay. So the sensitivity is going to be 4 to 20 times current state of the art. There is another metric you can use. Again, you have frequency on the x-axis, and again you have LOFAR, UGMRT, and JVLA in terms of the survey speed, which means how quickly can they carry out a survey of the entire sky, how much time does it take. So obviously shorter the time it takes, the better the telescope. By that metric, again, SK1 low, which was the dipoles, and SK1 mid, which was the dishes, will be 10 to 100 times faster than the best current telescopes. SK2 will be much faster, farther still, much faster still. So where are we going to build the telescope? We cannot build it in any inhabited place because the radio frequency interference from human activity is so strong that it would render the telescope useless. So you have to go to a remote site. So they're building the SK1 low, which are the dipoles. 130,000 antennas will be built somewhere here. There is a place called Murchison County in the desert in Western Australia where there is a district which is 20,000 square kilometers in size, okay, which is much larger than the city of Delhi, and the population of that entire district is 106 and falling. Okay, people are moving out. So there are approximate, so you don't measure density there in terms of people per square kilometer, you measure it in square kilometers per person. So it's roughly, I think, if you work it out, it's about more than 1,000, roughly of the order of 1,000 square kilometers per person. There is another, the SK phase 1 mid, the dishes are being built in, so unlike in the video where the 2 telescopes or the 3 telescopes were next to each other, after a lot of politics, which I can talk about offline, they decided to build it in 2 places. So the one in site in South Africa, and this is the southern tip of South Africa, this is Cape Town, this is 600 kilometers from South Africa, is a high semi-desert region known as the Karoo Plateau in southern Africa. Then when the dishes will come up, there will be 200 dishes of 15 meters diameter, reaching out to 150 kilometers from the center. Construction process will be initiated this year, but the things will start on the ground either hopefully by the end of next year. And the goal is to build the whole telescope, I mean the 10% telescope, for 675 million euros. Obviously, a project of this magnitude cannot be carried out both in terms of technological capability and financial viability by a single country. So the countries that are shown in this light blue color are the countries that have come together in order to build this telescope. Of course, Australia and South Africa are also participants. For the SK phase 2, there will be additional African countries that will be participants. But for the phase 1, it will just be Australia and South Africa. The work that is going to be done is organized currently in different consortia. Okay? This is groups of people who have come together and are working on the detailed design of some aspect of the telescope. So there are people who are working, for example, on signal and data transport. There are some people who are working on problems related to the dish. There are some people who are working on the data processing. There are some people who are working on the signal processor, which does the correlation, and so on. India leads a consortium of 7 countries, which is building what is called as the telescope manager. Okay, that is the heart and soul of the telescope. We'll come to that in a minute. About this telescope is so powerful that it can be used for a wide variety of science goals in a completely different areas of science. Like for example, you could do very, very reliable tests of general relativity. You could search for extraterrestrial intelligence. You could study magnetism in the universe. You could study the evolution of galaxies. This is the field of research that I work on. You could directly observe and study the first stars and galaxies, and you could study some of the biggest mysteries of cosmology like dark energy. How much better? So people did a simulation of what you would see. So what you see on the left is an image of a nearby galaxy as it has been observed with the VLA telescope, and this is a very short period observations. You can get, if you integrate for longer, you could get a somewhat better image with the VLA. But in the same amount of time, if you had the SK phase 1, then you would get an image like this. So you can see that relative to this, the sensitivity is better, which means you can see fainter objects over there, and also the resolution is significantly better. You can distinguish, things are not as blurred or hazy as you see. Yeah.
So what does black and white mean here? It's not visible still.
It's not visible, but it's just a map of intensity. So how bright is it? So when it's black, it means there will be a more amount of radio waves coming from there. and where it's white means there's no radio waves coming from that direction. That's all.
So all those tails are noise outside?
Yes, they're all noise, but how they're caused is a bit complicated, which I can tell you in questions. So what we are doing is the telescope manager component, which basically has to run this whole complex piece. Okay, so it starts off with trying to get a proposal from people on what they want to observe. That goes through a review process. Then that, if the proposal is accepted, then there is some amount of observation planning. The observation gets scheduled, it gets executed. This is probably the most difficult part because everything has to be synchronized, everything has to work properly. If something fails, then that observation may need to be repeated. And then there are all these sort of operations designer who's responsible for all the stages of executing the observation. The telescope manager naturally has interfaces with almost everything else. So it needs to, for example, talk to the dishes and tell them which direction to turn to. Okay? It needs to talk to the signal and data transport to make sure that the science data as well as the engineering data is being transported along the correct paths. It needs to talk to infrastructure to make sure that power and network, etc., is live on all the places where you need power and network. It has to talk to science data processing to tell it what is the configuration of the telescope so that the science data processing can optimize the processing to make sure that it's consistent with the settings on the telescope itself. It needs to interact with operators, it needs to interact with the scientists who's going to sit there and look at the observations. It also needs to look at the engineers who are making sure that everything runs efficiently. Particularly maintenance engineers need sufficient amount of drill down so that they can go and diagnose a problem remotely. Remember, you build this telescope in the most remotest places in the world. There's going to be no infrastructure, no roads, no nothing. So you're going to have to give the engineer the ability to figure out exactly what's wrong. And then they can go out with a line replacement unit. And if a piece of electronics has gone bad, they pull that out, they slide a new piece in, and you're good to go. So fairly complex exercise. And that is really made complicated by these prodigious data flow rates. And this is where we come to the scale of petabytes. Okay? So from the dish, you will generate 8.8 terabits per second. Terabits per second, which will need to be transported via an optical fiber network to the correlator, which is basically a multiply and add computer, an FPGA based computer, which can deliver about 50 petaflops. Similarly, for the low frequency aperture array, within every station will generate 2 petabytes a second. That gets decimated down to about 7.2 terabits per second, which gets transported again via optical fiber to the central signal processor. And then the central signal processor sends out 2 streams, 2 into 5 terabytes per second to the science data processor, which is basically a 250 petaflop supercomputer, which does all the computation that you need to go from visibilities to an image. Then the data get delivered to what we refer to as the SK regional centers, from where they're served to users. This data stream, as you can see, is very, very large. The final thing, the things that the astronomers want, is 300 petabytes per year. So you will build exascale archives in 3 or 4 years.
Just so that I understand it right, each dish is going to churn out 8.8 terabytes, or the whole farm is going to generate that?
It is going to be each 8.8 terabits per second. It is the entire farm. It's the entire farm which is going to churn. But there are only 200 of them in phase 1. So this is for phase 1, not for the video that I showed you. Right. So then everything goes to a processing unit, which we refer to as the science data processor, which needs to talk to the telescope manager. So this is the stuff that we are designing, and it has to get all kinds of parameters. For example, it has to know the telescope state. It has to know what is the exact configuration of the telescope when that piece of data was acquired. Because unless it knows that, it cannot process that data. So that we refer to as the telescope state, and it needs all kinds of other alerts. It also gets lots of inputs from the central signal processor. The fattest pipe that it needs is for transporting this visibility data. This is that 2 into 5 terabits per second that is coming into the science data processor. And of course, it needs to talk to the observatory because it needs to deliver image products and catalogs of sources, transient sources, and so on. The data flow diagram, I'm just going to flash this, I don't have time to get into the details. But as you can see, the data flow is extremely complex. There are places where things go back and forth. There are places where things are bidirectional. The data can flow and then flow back, and so on. And all this has to be done mostly by software, and is a fairly complex exercise. Once the data are processed in the science processing centers, so for the dishes, we will have a center in Cape Town, and for the low frequency array, we'll have another center in Perth, in Australia. And those data, as I said, will be delivered to a number of regional centers. We hope that India will be one of those regional centers. And from there to the users. The users don't access the regional centers directly necessarily. We will have a sort of common user interface that we will provide, like a science portal, which the users will log on to, they'll authenticate themselves, and then they will have transparent access to all the data that is sitting in the regional centers. So they might choose to look at some data which is sitting in China and combining it with some other data which is sitting in Canada, and the user does not need to know where the data is sitting. So as far as they're concerned, this is it's completely transparent to them where the data are sitting. They'll be able to combine data together and maybe build a visualization using resources maybe on a server in India. Okay, so I'm just going to go through in a few slides some of the sort of numbers that are related to computing for this telescope. So you need about 25 petaflops per second total sustain, and you need 200 petabytes per second aggregate bandwidth to fast working memory. You need 50 petabytes of fast working storage. This is not permanent storage, but something that is just like a scratch space. You need 1 terabyte per second sustained write to this storage. You need 10 terabytes per second sustained read from this storage. And quite peculiarly, you will perform 10,000 floating point operations per second for every byte that you will read from the storage. And all of this has to be done with a fairly tight budget of 5 megawatt per site. Currently, our design is exceeding this specification. So we can do all of this, but we can't do it with the flops per watt that we want. The main computing challenge from the point of view of the architecture of the high-performance computer for the science data processor can be encapsulated by this number. So we define a quantity called the arithmetic intensity rho, which is the total floating point operations per second divided by the memory bandwidth. The principal algorithms required by the science data processor, which is basically gridding of data and fast Fourier transforms, typically have a row of 0.5, and typical HPCs have a row of 5. Okay, so there is a factor of 10 mismatch between what a typical HPC will provide and what we want. So if you take a standard GPU architecture, an NVIDIA Pascal machine, that gives you these memory bandwidths and this floating point bandwidth. And as you can see, the ratio of the two numbers is somewhat higher than 5, and what we want is 5. So if we use a traditional HPC architecture, then we are going to have a computational efficiency of only 10%, which means if we want to do X amount of computation, we'll have to buy 10x hardware. Okay? And of course, we don't have the budget to do any such thing. Therefore, we have to work with the vendors to improve the memory bandwidth. So what we are looking for is not an HPC system per se, but a system called that is high performance data analysis, HPDA. So what does this system need to ensure? This must ensure that the data is available when and where it is needed. The CPUs must not be idling for the data to arrive, because that's where you will be wasting your compute resource. So the data must be in fast cache when it is needed. We need a framework that supports this, and members of the SK team, not us, because we are working on the telescope manager, but there is a group of about 20 institutions in 10 countries that are working on the science data processor. This effort is led by the University of Cambridge, who are looking at a variety of prototypes to try and solve the problem that we need to solve.
So the inefficiency that you just showed
Yes.
was primarily due to communication?
It's primarily due to the fact that your ratio of compute to I/O is completely different from what it is in a traditional HPC. We need a lot more I/O for the amount of compute that we need. So our compute is relatively simple. It is the I/O, it's the data volumes and the I/O that makes things very difficult.
Let me piggyback on that and just wonder, how does it compare to the LHC when the LHC is fully operational, when it has its downtimes?
Yes.
So when it's up and running?
Yes. So the raw data rates of the LHC are comparable. But there is one important difference between particle physics and astronomy. In particle physics, they are always looking for needles in the haystack, which means there are thousands and thousands of events. They are really interested in that one event which gave rise to a Higgs boson. Okay, they are not interested in the 99,000 other events that you. So what they have to do very quickly is identify the events that are promising and throw away the rest. So they're looking for the needle in the haystack. We are looking for the whole haystack. Okay? So that is why we can't throw away any data. So in terms of, although the raw data rates are similar, the computational challenges for SKA are far larger than what they are for the LHC. So the budget for building software is, out of that 675 million euros, is 90 million euros. This is not a very large budget. So again, we are going to be off budget on software. We need professional practices, naturally, for everything, for development, testing, integration, deployment. And we need to unify the processes across the worldwide team of developers. This is a major challenge, as we are finding. We are working in 7 countries just for Telescope Manager alone. It's a team of 35 people in 10 different places. It's a nightmare. Need world-leading expertise in a number of areas, and the delivered system will not be static. So that this telescope will operate for 50 years. And for most of those 50 years, the upgrades are going to be to the software, not to the hardware. Okay? So we will not deliver once, we will have to deliver multiple times. The scientific and software community in the regional centers will be a crucial form of input. So how are we currently organized? As I said, we lead the effort for the engineering effort for the telescope manager. We're making minor contributions to signal and data transport. We have already some collaboration with industry partners in India, specifically with TCS and Persistent. And in our group, we are working for the telescope manager with experts from radio astronomy centers in Australia, Canada, Italy, Portugal, UK and South Africa. In Australia, we're based in Canberra, in Canada, in Vancouver. So we actually work across 18 time zones. On the science side, a consortium of 15 research institutions and universities has been formed last year, and they're working on the science aspects. But this is relatively easy because the telescope is going to be ready in 10 years, so their focus is more on how can we train our students and postdocs to become effective users of this telescope when it arrives in 10 years. But they're also working on some precursor science and science with UGMRT and JVLA and so on. Opportunities for collaboration. So right now the detailed design phase is going on. There will be a set of critical design reviews. So the telescope manager design review is in April. That will be all the other elements, the dish, the aperture arrays, the infrastructure, all those elements will go through a set of reviews. If we clear those reviews, then there will be tendering for building the whole telescope in 2019. It's going to be such a big complex process, it's going to take 1 year to tender. Construction should start, if everything goes well, in 2020 and will take about 5 years. So by 2025, if all goes well, and surely it won't, we will have a telescope. But I think it is now this project is sufficiently advanced that it's very unlikely to be scrapped. We have already spent 200 million euros on this thing. It doesn't make sense to scrap it at this stage. So it's very likely to go on even if it is delayed by a few years. We are going to ask the government for participation at the 5 or 10% level. So if we get a 10% participation, that means there are 70 million euros worth of contracts that should come back to us. So the project has a policy that if country X puts in Y% of money, they should get Y% of the contracts back to them, so that they can grow their own industry. So doesn't look like we are paying money to some other country. So the Indian money, whatever it is, will be spent within India, mostly by awarding contracts to industry. Our strength is in software. So we are working with software companies already. We'll work with more in the future in order to realize this telescope. So we are also looking to partner with academia that can provide engineering expertise in areas where India will contribute. So it's a little bit of a chicken and egg problem at the moment, because we don't know what we will contribute. Therefore, we don't know who to approach to ask them whether they want to collaborate and so on. But it is very likely, my feeling is that a large fraction, maybe 70-80% of the Indian contribution will be in the area of software. It will very likely be a large fraction of it will be in the area of telescope manager, because that's the area in which we've already built up the requisite expertise. But nevertheless, there are a lot of discussions going on, and the exact modalities of participation will be worked out in the next 18 months or so. So this is sort of the time to get on board. These are two websites. This is the website of the SK, and this is the website of NCRA, where you can find more information. I'm going to, while I stop for questions, I'm just going to play a video, which is another video made again by the Australians on the sort of data transport challenge of the SK. Okay, so
the goal is just to collect the data or to utilize it somehow as well? I mean, I didn't see anything how you are going to utilize the data.
Yes, so I didn't focus on that aspect. So I had just one slide which talked about the science. So I showed you that early slide where I talked about how the universe evolved. Okay? A crucial phase in the evolution of the universe, which we don't understand today, is how did the universe go from being completely neutral to being completely ionized. Okay. This phenomenon occurred between 12 and 13 billion years in the past. So it's an extremely distant event, very hard to detect except with very sensitive radio telescopes. So what we are trying to do is to build a key science project that will focus on answering this specific question. So it's called the reionization of the universe. okay, or to study the epoch of reionization, and that will be done. So this just represents these optical fibers which will be laid under the ground. So remember, you have to have a network connection to every large dipole. Okay? And there will be lots of stations, the data will be aggregated together and sent off to Perth. And this is where you will have a supercomputing center, and data is flowing everywhere in Australia. For the escape phase 2, they will have an undersea fiber link to Tasmania and to New Zealand, where also again you will have more data. So this was an advertising video that the Australians had produced. Anyway, yeah, so coming back to that question, so we will study the neutral hydrogen evolution of the universe in exquisite detail using this telescope. That is just one aspect. There are other things like magnetism. Magnetism, we know there is magnetism everywhere in the universe, but we don't know how much and what role it plays in all the physical phenomena that you observe. Magnetism can be best studied by polarization observations in the radio. Right now our telescopes are not very sensitive enough to permit those kind of observations on a large scale. With the SK, we can do them as a matter of routine. Right now we have to invest a lot of time and effort. It's a very difficult exercise to do it. Here it will be almost automatic. So there are many other aspects of science which I didn't talk about consciously.
How would you said that this escape would also help in when it tests on the relativity and gravitational, how can
Okay, so gravitational waves. So one thing that you can do for the study of gravitational waves is you can detect them indirectly by timing pulsars. So you see pulsar is a rotating neutron star. It's going to give you a pulse every fraction of a second or whatever. Now, if a gravitational wave passes through the galaxy, then it perturbs the space-time just enough to cause a delay in the pulsar arrival signal. If you observe many pulsars together, that constitutes a pulsar timing array, that can actually give you even information about which direction the gravitational wave came from, what was its amplitude, and so on. So you have to do this over many years. You have to basically, the exercise is very simple. You have to keep timing the arrival pulses from many millisecond pulsars for a very long period of time. 5 years, 10 years, and then you will start detecting gravitational waves. And once you have everything nicely calibrated, you can detect it. Strong tests of gravity, general relativity, will be possible because you will be able to observe rotating neutron stars, which are the pulsars, in with much greater sensitivity than you could observe previously.
But then you'll have to keep observing, keep timing them, right?
For gravitational waves, you will have to keep timing them. But there are also tricks. So for example, while you are observing, you could have a sort of pulsar observing mode on all the time. So suppose I am observing a galaxy in a particular direction. Suppose there is a pulsar nearby. I could also record the signal from the pulsar at no additional cost in time of the telescope. So this kind of exercise can be sort of endlessly done. There are already some piggyback experiments that are trying to do this.
Even if any kind of observing, you just have your background.
It's automatic, yeah. It gets automatically routed. So you get more data than anyway for free. Yeah.
Yeah, so in one of your block diagram I have seen that this SK manager is providing a sky model to the data processor.
Yes.
What is that sky model?
Okay. So in order for the science data processor to work optimally, it helps if it has a model of what the sky looks like. Okay, which means what source is where. Right?
So
Now,
so is the data processor is doing any estimation and using the data and the model?
no, it is using the model as a starting point. It's like when you are trying to, let's say, minimize a function. It helps if you can give the initial values that are a reasonable good first guess, so that you converge to the right point. If you give it something way off, then it will take much longer to converge to the right point. So the sky model is basically just a catalog of sources on the sky that have been previously observed either with the SK or with some other telescope, that can be used as a starting point for the modeling of the source intensities on the sky. Yeah.
You said there was a lot of politics in deciding South Africa and Australia.
Yes. So yeah, let me tell you briefly. So what happened was there were two serious bids for building the telescope. South Africa said we will build it in South Africa. Australia said they will build it in Australia. There were a few other bids earlier which were not on the short list. So final short list was South Africa and Australia. Now both these countries became very excited about winning this. It's like two countries competing for getting Olympic Games or something like that. Okay, if both of them started investing money in infrastructure, they said we'll build roads, we'll build this, we'll build power lines, this, everything. And they even started under the assumption that it has almost come to their country. Then the ministers got involved. So the science ministers of South Africa and Australia and so on, they got very political about it, which means they started talking to other people. Whenever they visited countries, they started talking to them. They even instructed their consulates in various countries to start talking to the other partner countries, make phone calls, try to influence the decision in their direction. So international committee was set up to choose a site, and in the background, while that committee was working, this political activity was going on. And I don't know the details of what eventually happened, but suddenly we learned that they have decided that there is simply no way they can build it in one place. They'll build it in two. And initially the big argument against building it in two was that you are wasting money by building roads twice and power net lines twice and so on. Why should you do that? The response from South Africa and Australia was that we'll take care of that. So then that argument went away, and technically the sites are not too different. In terms of the pure radio astronomy perspective, they're not too different. Financially it's going to cost more, but not to the project, because these individual countries have undertaken to provide infrastructure at their cost.
So is it also advantageous to have, like South Africa, Cape Town and Australia, they are quite widely separated?
Yes.
On longitudinal scales. So isn't it advantageous to have two pointers of a telescope? So one of doing one part of the sky and the other of the.
That was always possible. So because even if you had sighted them in one location, there is no reason for both telescopes to point in the same direction.
So there is always some part of the sky that's below the horizon for one part of the Earth. That's not below the horizon for another part.
Yes, but you are assuming that this detection will be critical, and it is time critical in the sense that if it can't be delayed by 6 hours. There are always phenomena that are going off. That way you should have why not 2, why not have 3? Okay. So, but most astronomical phenomena don't suffer too much by being delayed in observation by a few hours. Yeah.
So you said India's or your collaboration is involved in this telescope manager.
Yes.
Could you give us some, thoughts on what new research output that's going to generate? Like, I don't know, I'm naive here, but
This
I want to make it
this is not going to. So this is actually not part of my research at all.
Sure.
Okay, and it's not part of anybody's research. So what we are doing now is basically a detailed design based on a concept design that we produced 5 years back. So I was very heavily involved in that part, producing the concept design. But I have been less active since the time of the preliminary design review and into this detailed design phase. So we don't, when we say we design the telescope manager, this is not a research problem for us.
You could still make a new kit, I don't know, something like, some new things that provide software engineering.
Yes, so I'll give you an example of some of this thing. So one of the ideas about developing this software is that the software has to be easily reconfigurable. Okay. Now there are ideas in computer science that promote this idea. So you basically have some kind of specification driven system where the core code remains the same, but you change some configuration parameters somewhere, you change the specification of the telescope, and everything runs as is. We have applied this kind of system to a telescope monitoring and control system. And we know it works because the people who developed this at the Tata Research Design and Development Center, who are working with us, they initially developed it for the ITER system, which is the International Thermonuclear Fusion Reactor that is being built in France. So they built it in such a way that, okay, this is a fusion reactor, but that is specified in the specification. The monitoring and control system should be able to abstract out the commonality of any control monitoring problem. So they have been able to largely successfully separate out the specification layer from the core monitoring and control system. So what we will therefore be able to do if this works is take the ITER, a monitoring and control system for a fusion reactor, and apply it to a radio telescope by just rewriting the specification layer. So now whether this will work or not is an open question. So what we've done is not R&D from scratch, but we've done several instances of taking ideas that have been developed elsewhere and adding our own contributions to that. And there are several other examples like this, but this is
Is there any formal proposal has been given to Government of India as you have said?
Not yet. So, but we are beginning to write it. So, I think in the next few months we'll submit.
And just a comment, since LHC, as you have said, the data is raw, it's 100 petabytes that we analyze as the particles.
Yeah.
So, and the very high luminosity LHC is going to
Grow it even more.
And the data mining and the data processing is much more complicated. Probably what I understand from what
Here, you mean, not in the LHC.
in the LHC.
In the LHC is more complicated.
No, it will be in the next phase.
In the next phase. Okay.
Yeah, because they are going to be high luminosity, high intensity.
So how do we stay in touch with you and this project?
Okay. I wish I had a simple answer to that. Okay. You can stay in touch with me by sending me email. But the problem is I get so much email these days that I'm not able to respond. What we will put out eventually is a way for a sort of call for proposals for people to participate either as an academic collaboration or as a industry partner. So what we did last time when we did work for the detailed design, instead of public tendering everything, what we did was we first technically qualified a group of industries. So we had a set of specifications of what we required the particular industry to provide, and that was publicly announced, and then we received proposals in response from some industries, and then we had evaluated those proposals. Basically, we were trying to see if a particular industry, not a particular industry, a particular company had the capabilities that we were looking for. And if they matched those capabilities or exceeded them, then we pre-qualified them, and then limited tenders were issued to get the work done. So that will also happen. So there will be another opportunity now for industries to get qualified as well as academics to join collaboration. If you're interested in the science side, then the SK India Science Collaboration is the place to join. And there are many people who joined that.
But I think they're asking, sorry, I should talk for somebody else, like, are there internship opportunities?
Oh God, okay. So, internship opportunities. So one of the problems with this whole game is that the required domain knowledge is sufficiently high that if an intern comes in, the intern will learn a lot, but we will not learn anything from the intern, because by the time they get to a stage where they can actually begin to contribute, it's time for them to leave. So it will be hard for us to support internship opportunities over here unless there's some kind of long-term collaboration or a longer-term commitment. So for example, if there are students who want to join our PhD program, for example, and then they say they want to work part of the time on this telescope, then that's a completely different level of commitment, and that can be easily supported. It's very hard for us to support interns who want to come for 15 days or a month or something and work.
So what is your definition of long-term internship?
3 months or more.
So they can easily do that, they have enough time, and if genuinely interested one can take semester off also for internship, and people have done it in the past. It's not very advanced.
Semester or year or also.
So they can do that. Okay, alright, so if there are more questions, it should be available in the CCD, but right now we will just stop here because it's already 15 minutes past 5. Let us thank Yogesh for wonderful time.
Okay, thank you.
Alright, so those who want to talk with Yogesh will be available in
Yeah, sure.
So he will be available in the